My name is Marin Soljacic. I'm a professor of physics at MIT. I work in electromagnetic phenomena in general, but with a particular focus on nanophotonics and also on nonlinear optics. Typically, when you have a localized potential, what you will see is that there is some set of localized bound states which will be discrete, and then above them in energy there exists a continuum of extended states which are not localized. So that's quite typical. So a natural question is whether within this continuum of extended states there can be at least one, maybe many, but at least one eigenstate which is localized, but it coexists with all of these extended states inside of a continuum, yet doesn't mix with them. And that's called embedded eigenvalue, and it was in physics, to the best of my knowledge, first proposed and investigated by von Neumann and Wigner in 1929. So first of all, light trapping is necessary for probably most optical devices you would want to build. For lasers, for optical fibers, let's say even for solar cells, you have to have a way to confine or, if you want, trap light. And typically you do it with mirrors, right? So there are metallic mirrors, photonic crystal mirrors, mirrors due to total internal reflection. And what is common for all the mirrors that we knew up to this point is that they operate based on the fact that light encounters a surface beyond which there are no modes to which the light can couple to. Because light has no option to what it can couple to, it has no other option but to reflect. So pretty much every mirror that we were aware of up to this point operates based on this principle, that light, when it encounters this surface, it has no modes to which it can couple to. In contrast, this novel way of light trapping is quite different, because light very much does have modes to which it could couple to, and the reason it doesn't couple to them is because it eliminates its own radiation into those modes. So it's quite a different way of light trapping, and you know, whenever you discover a substantially different way of doing something, then quite often at least some applications are enabled. And at this point we are more focused on investigating novel science associated with it, and then the next step would be to think about, okay, what are the most suitable applications for this? We actually did these computer simulations because we wanted to investigate some more conventional, well-known ways of trapping light, and we wanted to investigate some of their properties. And then my student, Qiawei Xu, noticed at some point when he was investigating that this very strange thing happens, that you have this localized bound state where you really don't expect that you should have it. And it actually took us longer, some time, of the order of a few weeks, to figure out what is going on, what is the reason for it, and that we really discovered something quite unusual and novel compared to other things that we knew. The first response is, go check whether you did something wrong, right? So once we eliminated that the things are wrong, then we try to explain it in terms of unusual manifestations of the phenomena we already knew. And there is a number of those that we tried. And when we saw that none of those can explain this at all, then we knew that we really had something new. And that's when we really, started investigating this in greater detail. We understood that we need a new explanation, new theory, and that it means that it's basically, quite different than the things we knew before. So we implemented them in a 2D periodic photonic crystal slab made of silicon nitride on silica substrate, and then we also immersed the whole thing in liquid, which was index matched to silica, in order to make the system have reflection symmetry, which is a requirement in order to observe this particular kind of states. And then we observed, basically measured the reflection of laser beam as a function of angle and as a function of incident wavelength in order to observe where those states are. But the fact is that it's not just restricted to photonic crystals. In fact, you should be able to observe it in many different periodic media, probably even beyond periodic. So you should be able to see it, for example, in metamaterials, and even in systems beyond optics, like in acoustic systems. So it's not necessarily tied to photonic crystals. But the reason why we did it in photonic crystals is because photonic crystals give us this great opportunity to tailor the flow of light, and we found it convenient to work with them. So just to implement a laser or to demonstrate sensing, I don't think it will be very challenging in the sense that providing it with some gain and maybe a little bit of feedback in case of lasers, you should be able to see lasing or you should be able to demonstrate sensing. But in order to make this into a truly useful device, which operates according to some figure of merit better than other similar devices, so that it will be truly useful for a particular application, that will require more work and investigation to answer that question. That is, for which particular applications is this really useful, very useful compared to other ways of doing it. I very much like the opportunities that photonic crystals offer in order to tailor the flow of light. So photonic crystals are often called semiconductors for photons, in the sense that semiconductors enable integration of electronics. Photonic crystals are rightly thought to be one of more promising ways or more important ways to enable the eventual integration of photonics. Since they were first invented in 1987, there was a lot of theoretical interest for about a decade or so, but there were huge challenges fabricating them. Then, as fabrication methods matured, so people could really build these things that people were all excited with, brought a new level of excitement. At this point, the fabrication methods are sufficiently mature that people started implementing even useful devices with photonic crystals. So I think it's been growing to become a more mature field on one hand. On the other hand, it's realized now that it is still so rich from the point of view of science that there are still so many interesting, even more exotic science questions to answer, for which we will need yet new fabrication methods and which will only 10 or 20 years later lead to useful devices. But it's quite a rich field. There is so many things to do, basically, I think.